In 2004, two scientists at Manchester University peeled a layer of carbon atoms off a pencil using sticky tape. What they found was a material nobody thought could exist. 1 atom thick, 200 times stronger than steel, and more conductive than copper. They won the Nobel Prize 6 years later. For 20 years, graphene was trapped in laboratories. Too expensive, too difficult to make at scale. Then something changed. In 2025, global graphene production hit 23,000 tons. The price of graphene film crashed 73% in just 2 years. The material that was going to change everything is finally doing it. So what actually is graphene? Take a block of graphite, the black material in every pencil. Now imagine peeling one single layer of atoms off its surface. That layer is graphene, a hexagonal arrangement of carbon atoms, 1 atom thick, the thinnest material that has ever been discovered on Earth. The strength comes from the carbon-carbon bonds, the strongest chemical bonds in nature. In graphene, they form a flat, flexible sheet. You could cover an entire football pitch in graphene, and the sheet would weigh just 6 grams. Stronger than steel, lighter than almost anything. Graphene is also nearly invisible. It absorbs only 2.3% of visible light. That transparency, combined with its electrical conductivity, makes it ideal for touchscreens, solar cells, and electronic displays that are fundamentally better than anything we use today. If graphene is so extraordinary, why did it spend 20 years stuck in laboratories? The answer is manufacturing. The original method, peeling it off graphite with sticky tape, produces perfect graphene, but only tiny flakes a few micrometers wide. You cannot build a computer chip with a postage stamp. Early attempts at scaling up production created graphene full of defects, missing atoms, irregular bonds, contamination. Each defect destroys the extraordinary properties that make graphene special. Making graphene cheaply was easy. Making it perfectly at scale was the unsolved problem that kept it in labs for 2 decades. Chemical vapor deposition solved the problem. In a CVD reactor, methane gas is heated to over 1,000 degrees Celsius above a copper foil. The methane breaks apart. The carbon atoms land on the copper and self-assemble into a perfect hexagonal graphene lattice. Large, continuous, consistent, scalable. In 2025, a Cambridge spin-out called Graphic raised 25 million euros to commercialize graphene photonic circuits. Paragraph raised $55 million to build wafer-scale graphene electronics. Both are building on the same breakthrough. The first functional graphene semiconductor ever built, achieved in 2025. The geopolitics of graphene is as intense as the science. China holds more graphene patents than any other country. Samsung alone has filed approximately 500 graphene patent families, more than any other company on Earth. In 2015, Chinese President Xi Jinping personally visited the Manchester Graphene Laboratory during a state visit. The UK pioneered graphene research, but found itself in an uncomfortable position. Companies spun out of the National Graphene Institute ended up with majority foreign ownership, triggering accusations of technology transfer. Nobel laureate André Geim, the man who discovered graphene, described it as money spent on buildings rather than science. The most immediate application is batteries. Graphene added to lithium-ion anodes dramatically increases the rate at which a battery can accept charge. Early commercial graphene batteries can charge to 80% in under 10 minutes. That is 4 times faster than the best conventional lithium-ion cells available today. In semiconductors, graphene transistors have been demonstrated running 100 times faster than silicon. Graphene electrons travel as massless Dirac fermions, quantum particles that never stop conducting. In 2025, the first functional graphene semiconductor was built at room temperature, removing the last fundamental barrier to replacing silicon chips. Graphene can also filter water at the molecular level. Nanoporous graphene membranes allow water molecules through while blocking salt ions, enabling desalination at a fraction of current energy costs. MIT researchers demonstrated graphene membranes requiring 100 times less energy than reverse osmosis. Clean water from the ocean with a single atom layer. Graphene was discovered with sticky tape in Manchester in 2004. In 2025, China leads its production. Samsung holds the most patents. A UAE sovereign fund is backing UK graphene semiconductors, and the first graphene transistor is running. Who wins the graphene race determines who controls the next industrial revolution.